Hello all. So welcome to this new lecture of the course EV Vehicle Dynamics and Motor Drives. So in the previous lecture we have seen the controller design for the current and speed controllers of the control loop of the induction motor drive, and we have proceeded on basis of the model of the squirrel cage induction machine in the rotor flux oriented frame of reference. From here we have gone to understand how the whole block diagram is going to look like, and we have seen that some of the nonlinear terms can be cancelled through feed forward terms, and if we treat them as the disturbance, we can create a simple linear system which can be designed using PI controllers. So we have two inner current control loops within the flux loop and speed loop given over here. We have IMR coming as a input in the computation of torque, so which is why we have involvement of the current, flux and speed within this structure, and this is where we go for defining the bandwidth in a manner that we can design the controllers independent of each other. So we are defining the bandwidth for the current, flux and speed control loops, and we are setting a criteria that the bandwidth for the speed control loop should be 1/10 of the flux control loop. So we are trying to establish that before there is any change on the speed controller, or before there is any appreciable change on the speed, our flux is ultimately settled to its final value, and further the flux is also 1/10, no, the bandwidth for the flux control loop is also 1/10 of the current control loop bandwidth. So once again we are trying to establish over here is that the currents are settled before there is any appreciable change on the flux, and then we are keeping the current controller bandwidth as 1/10 of the switching frequency. So this is how we are able to correlate different bandwidth for the given system. So we have taken an example as well, that if the switching frequency is somewhere around 5 kilohertz, we are going to see these kind of numbers in the bandwidth of the system. So bandwidth for the current control loop is going to be corresponding to 500 hertz, and bandwidth for the flux control loop is going to be corresponding to 50 hertz, and bandwidth for the speed control loop is going to be corresponding to 5 hertz. So this is how the numbers can be decided, and then we can take up the design of each controller independently. So first we have considered the current controller, and we are finding that there is one slow pole which is available in the system, which can be cancelled through the zero introduced by the PI controller, and we can further design the bandwidth of the current control loop equal to the 1/10 of that of the switching frequency. So this is the correlation, and then we have two equations for deciding the value of Kp and Ki, which can be used for writing down the D and Q axis current controllers. Now eventually the current control loop settles down to a first order system where reference is provided, and we have the output which is kind of having a response of first order system, and this basically comes as a subsystem within the flux control loop. So we are keeping 1 plus s tau I as a subsystem within the flux control loop, and we have the rotor time constant and the PI controller as well given in the same control loop. So we have tried to simplify, and we have tried to take a combination of the two poles in such a manner that we are having an equivalent pole in the system. So this order of the system gets reduced, and we have a simpler system for deciding the KPKI values. And once again, taking the slower pole, we are using the zero of the controller to cancel out this pole, and then deciding the bandwidth of the remaining plant on basis of the criteria set in the previous slide. So we have said that the bandwidth of the flux control loop should be 1/10 of the current control loop. Now once again going ahead, we have taken the speed control loop, and we have considered the current ISQ control loop as a block, as a subsystem within that. Then we have the PI controller and the mechanical subsystem. We also have a filter in the feedback path, So altogether, the open loop transfer function of the speed control loop is having several sub-blocks over there. Now, because of the presence of a double order pole at origin, we are finding that the system is inherently unstable, and hence the pole zero cancellation method is not going to help in this case. So which is why we need to have a different method, for example symmetric optimum method, which can be used to gain some phase margin in the system. So if we analyze the Bode plot of the system, what we are finding is that the open loop transfer function for the uncompensated system is going to have magnitude plot falling at minus 40 dB per decade slope, and if this is allowed to cross the 0 dB line, the gain crossover frequency, the phase is going to remain at minus 180 degree. However, for a stable system, we need some positive phase margin in the system, and which is why we need to have the arrangement of zero and pole in such a manner that the gain crossover frequency is basically witnessing a kind of reduced slope, something like minus 20 dB per decade. So in that case, we will have some improvement in the phase going above minus 180 degree and minus 180 degree, and then we will be having some positive phase margin at the gain crossover frequency. So once we are placing the pole and zero symmetrically, we can be sure that the phase margin is going to be the best possible in this condition. So three conditions we are going to utilize in this case for designing the Kp, Ki and A, three unknowns in this system. One, the ratio between the different pole locations, which is basically given by A. Secondly, the phase margin, we can take a phase margin of 45 degree for keeping the system stable, and the magnitude at omega b omega point to be equal to 1 to ensure that we are having the gain crossover frequency at this given frequency, at the desired frequency. So these are the three conditions which are used, and we are able to design the controllers of all three systems over here. Further, we have tried to see the complete block diagram to understand the different types of vector control which are possible, and we have given the software and hardware combination which is required for operating the squirrel cage induction machine in vector control mode. So we have reference provided for IMR and omega. IMR reference could be external or it could be internally given, whereas omega m is the reference set by the user. Then we have IMR loop operating within this, and it is eventually generating the voltage VSD star, VSD reference. The omega reference, omega speed loop, or the omega loop is basically operating to generate the VSQ star reference voltage for the system. Eventually, this D and Q axis reference voltages are required to be converted to three-phase modulating signals, which are compared with the triangular carrier, and we have the PWM signals generated for different devices. So since we are dealing with two-level three-phase VSI, so we have 6 output coming over here corresponding to the gating signals of 6 devices. These are basically fed to the gate drivers of the inverter, and which eventually generates the voltage at the terminal of the motor for achieving the desired current and speed. Now we have seen that in this whole system we require several feedback quantities. So we have current feedback, we have flux or IMR feedback, and we have omega m feedback. These quantities, and in fact the current and omega and IMR are also involved in the feed forward terms. So we need to have some measurement or estimation of these quantities. That can be achieved through some sensors which are either mounted physically on the system. Say for example, we may have current sensors. Typically we have Hall effect current sensors used for this purpose. We may measure either 2 or 3 or all 3 currents based on what type of system we are dealing with, and then eventually converting that three-phase system to three-phase current to DQ, ISD, ISQ. Now, once we have ISD current available with us, we can use the rotor flux model and we can get IMR value. Now, once this value is achieved, the flux control loop can run sufficiently. However, for the speed, we have option of using speed encoder to directly achieve the value of omega m, to directly obtain the value of omega m, or we can look for other methods. So in case we are having the speed encoder available in the system, we are calling it a censored vector control, and then in that case we have the measurement of slip speed. The slip speed is added to the mechanical speed to generate the synchronous speed, which is eventually used to generate the unit vectors which are required for all the RYB to DQ or DQ to RYB conversions. So this is how the whole system is running. However, we have seen the option of that we can get rid of the speed encoder due to multiple reasons. One of the reason could be that the motor might be sitting in some say polluted area or some hazardous area where keeping the encoder outside may actually degrade the performance of the system. It may sometimes create error in the encoder, and hence it may be advisable to estimate the speed and then go on doing the whole control what is shown over here. So such method can be called as sensorless vector control, and this is what we are going to extend today. Now, to achieve sensorless vector control, the important factor what we need to have is basically estimation of rotor flux. And when we are saying that we are going to use this estimated rotor flux for computation of speed, unit vector, etc., we are referring to the rotor flux vector measurement or estimation in the stator frame of reference, which is usable, which means eventually we are looking for components of rotor flux in the alpha beta, stationary alpha beta frame of reference. Now, as stated earlier, the rotor flux can be expressed in terms of the magnetizing flux and the rotor leakage flux, which is LLR times of IR, and the equation is written in the stator oriented, the stationary alpha beta frame of reference. Now, because psi m can be written as combination of IS and IR, we can segregate the terms related to different currents, stator and rotor currents, and then we can write this equation in terms of Lm IS plus LR IS in the stationary frame of reference. Now, because the quantity which we are trying to estimate is the rotor flux, the measurable quantity available is IS. However, IR is still unknown quantity. So we would like to have replacement of IR from the estimation of the rotor flux. So we'll express IR in terms of rotor flux and stator current. And we are going to use the next equation, stator flux equation, where we can plug in the value of IR from this previous equation. To have the stator flux written in terms of rotor flux and stator current, we can rearrange this equation to obtain equation for rotor flux. Right. So once again, this term, if we refer our previous lecture, is basically given as total leakage coefficient. So our rotor flux can be written in a compact manner in terms of the scaled value of psi s minus sigma ls times of is. Now this is interesting. If we are trying to compute the value of rotor flux, eventually we need to compute the stator flux, and then by subtracting the scaled value of is, we can obtain the value of rotor flux. Now if we notice from the equivalent circuit, there are different components involved. So we have applied the voltage Vs. There is current flowing here as Is. Now the flux associated with LLS is basically our stator leakage flux psi ls. The flux associated with Lm is our air gap flux. So sum of these two flux is what we are referring as our stator flux. So which means that if we are trying to compute the stator flux, we are going to have combination of psi ls and psi m, which also means that eventually this is on account of the voltage applied across these terminals. This can be called as Es. So Es can be written as Vs minus ISRS. Now psi s can be obtained by integrating this voltage Es over the given period of time. So at this point now we can take out the components of the rotor flux vector and stator flux vector in the alpha beta frame of reference, and we can eventually draw the block diagram for this whole exercise. So we have the input voltage corresponding to alpha axis available with us, Vs alpha, where we are subtracting the drop in the resistance, and eventually this is generating Es alpha, which is going to be integrated to generate our stator flux along the alpha axis. Now we need to subtract the scale Is alpha to generate the scaled psi r, and by multiplying the appropriate gain Lr by Lm, we can generate the alpha coefficient, alpha component of the rotor flux. Similarly, we can have the beta component also generated in this manner. So this method gives us a simple way of estimating the rotor flux on basis of the inputs available, say the voltage applied across the machine and the current flowing in the line of the machine. So we can have psi r alpha, psi r beta components to get the unit vectors which are associated with that. So we have cos rho unit vector given as the scaled alpha axis of the rotor, alpha axis component of rotor flux, which can be essentially scaling the magnitude of the alpha axis component. Similarly, the next unit vector can be taken as scaling of the magnitude of psi r beta. So this provides us the necessary unit vector which are required for the conversion of RYB to DQ or DQ to RYB. Now, moving ahead, we would like to estimate the speed, rotary speed of the machine. So it should be understood that once again, the unit vector what we have estimated has information about omega s, the synchronous speed. So taking the fact that time derivative of sine rho is going to give us omega s times of cos rho, and time derivative of cos rho is going to give us negative of omega s times of sine rho. So we can arrange these two terms in a manner that we can take cos rho times of ddt of sine rho subtracting the sine rho times of ddt of cos rho. So this would eventually give us omega s times of cos square rho plus omega s times of sine square rho, giving us as omega s. This is important from the point of view that when we are implementing on a microcontroller, we have the value of cos rho and sin rho available at the instant. We are never having a full waveform available with us. So we can take the present value and maybe the previous value to compute the derivative of these terms. So this is where it becomes important, and we use these derivatives as the difference equations. So when we are talking about the practical estimation of speed at this sample, say nth sample, we are talking about taking the value of cos rho at the nth sample, value of sin rho at the nth, and then subtracting the n minus 1th sample over a time period which could be our sampling time, and then subtracting the next part of the expression, nth sample of sin rho multiplied with the difference equation corresponding to ddt of cos rho. So this will provide us the information of speed at every sample. We need to store one sample in advance to obtain the value, to understand that how fast the sine rho and cos rho are changing their values. Now, because there is derivative involved with this process, we have the difference equation available over here. So many a times this process could be very noisy. So we may have omega s generated that could be consisting of lot of high frequency noise. So this high frequency noise should be filtered before we actually use it for our feedback control system, and this is where our feedback filter is going to be useful. So we have suggested that we are having a low pass filter in the speed feedback. So our filter is going to be helpful in removing this as well. Now there are certain limitations when we are trying to have the estimation of flux by having pure integrator over here. Numerically it creates problem. So when we are trying to compute the integration of a pure sinusoidal waveform, we may have problem of DC drift. For example, for the running waveform which is providing us the information about ES alpha or ES beta, we may end up getting the rotor flux which is drifting slowly on one side. It could be positive drift or negative drift. This is on account of the numerical issue which is associated with the pure integrator. Now this problem is purely mathematical, so we need to have some arrangement to get rid of this drift. So we are having pure integrator which can be represented like 1 by s. So instead of using pure integrator, we may have a non-origin kind of integrator, say 1 by s omega c. So this structure is different from filter. It is not a filter structure. We are still having kind of integration option, a kind of integration operation happening over here. However, the pole is not sitting at origin same as pure integrator. So this omega c may correspond to a low frequency, say 2 hertz to something around 5 hertz. Now what happens on account of this block? So once we are feeding our ES alpha, for example, to obtain psi S alpha, there is some correction which is getting involved in this process. So for example, if we try to expand this block, and psi S alpha can now be written as ES alpha minus omega c times of psi S alpha divided by S. So which means that the block diagram which we have drawn with pure integrator will get modified with a correction factor, and this correction factor is basically dependent on omega c. Now we can further continue with the rest of the model. Similarly, we can have the beta axis computations as well. So pure integrator is basically replaced by this block which is shown within the dotted region. Now, yes, some of the problems are definitely solved with this process. However, still there are some issues which are involved with this. For example, when we are trying to set a value of omega c, we are somewhere restricting the usage of this model for low speed regions. Restricted for low fundamental frequency. For example, if we are setting omega c corresponding to say 2 hertz, and we are trying to have estimation of rotor flux at a fundamental frequency of 1 hertz, this may not be very accurate. So there could be errors in the computation of the rotor flux, and which is where our sensorless vector control may suffer at low speeds. Now we can have some corrections in the model which we have given with the pure integrator to get rid of these problems. So eventually we are computing our error voltage which requires a correction for stopping the DC drift and other issues. And then we need to have the same process. We have integrator and then which is generating the psi s alpha. The rest of the model stands as it is. Now, if we notice, we also have an estimate of IMR available within our system. And the magnitude of the rotor flux is basically Lm times of IMR by definition. So which is why we have a different way of estimating the rotor flux magnitude, and then since we are computing the unit vectors cos rho and sin rho, the magnitude can be multiplied with the unit vectors to obtain the exact component of the rotor flux. So if we take product with cos rho, we will be basically generating another estimate of psi r alpha, which I can call as psi r alpha star. Now there are two estimates available for the same quantity. So we can compare these two, and the error can be used as the correction factor for improving the DC drift. So some constant say k phi can be taken over here, and the error is basically fed back to the voltage so that there is no DC drift coming up in the system. So this could be another way of estimating the rotor flux, which is not bounded by any kind of corner frequency or any cutoff frequency for the integrator, and this can have accurate estimation at low speeds. So these are some of the methods which we can use for estimation of rotor flux and then the unit vector on basis of that. So eventually we have three methods given over here. First, where we are having the pure integrator. Second, a correction on that, and when we are having a cutoff frequency based integrator. And then third, where we have the feedback and then the correction factor given for the IMR. So either of the methods can be used. There are many more models, many more observers available in literature. those also can be used for estimation of rotor flux. Now this is where we are done with the computation of the rotor flux or any other estimation which we are requiring for operating the vector control of the synchronous of the squirrel cage induction machine. So now the next task comes where we are going to decide the reference and saturation limits for the controllers. So as we have mentioned that IMR reference can be generated internally as well as externally. However, the value is not very straightforward to be known. The omega m reference can be given by the user based on the maximum rated speed, and then we can have a reference set within that or beyond that, but restricted by the mechanical rotational speed capabilities. The reference for IMR should be computed on basis of what is the rated IMR value for the given machine, and that once again has to be computed on basis of the model of the machine. For example, we may have nameplate rating where torque, rotational speed, number of poles, slip speed, these parameters may be mentioned, voltage, current, and then we can have the parameter estimation for the machine which can provide us the other circuit related parameters, for example RS, RR, LLS, LLR, LM. Now using these things we can compute the required value of IMR. So as I said, we have already derived the value of omega slip in terms of ISQ and IMR, and on the other hand we have computed the electromagnetic torque in terms of KT, IMR and ISQ. So we can use this information and nameplate rating to compute the values of ISQ and IMR, the rated values of ISQ and IMR for the machine. So we can plug in the value of ISQ from this equation to the slip, omega slip equation over here, or vice versa. And then the rated value of IMR can be given in terms of tau e, KT, omega slip and TR. So once we have this value, we understand that how much reference can be set for the IMR, for the rotor flux. And then using this information, we can always compute back what is our ISQ, rated ISQ for the system. So this gives us information about how much current reference should be generated by the speed and flux controllers. So if we are trying to put a cap on the ISD reference generated by IMR, we can follow the rated value of so we can have saturation, which is basically also cutting off the integration process, and this value of saturation could be as per rated IMR. Similarly, once we have the speed control loop running. This would eventually generate the reference for ISQ, where this value has to be limited to a number which is corresponding to the rated ISQ value of the system. And when we are restricting, we are saturating the value of the reference, we also need to stop the integration process at the moment to avoid the wind up problem in the system. Now, once these references are generated and we are going for next level of PI controllers, we are eventually generating the voltage reference values. So these voltage reference values can also be obtained on basis of the model of the machine. So we have already given the equations. Now it should be noticed that when we are referring to the reference values for VSD and VSQ, we are essentially talking about the steady state values of VSD and VSQ from the model, which means that under the steady state conditions, the terms which are having the derivative factor would reach zero value. So the remaining factors which are available over here would be used for computing the saturation limits for VSD and VSQ. Now, it may happen that sometimes while computing the value of VSD, it may come out to be less than 0, which means a negative value, which is all right. So some of the machines or some of the systems may have this kind of value. Generally, we would find VSD going to a negative value. So this is what we require for computation of the saturation block limits while also stopping the integrator at that point. So overall, in this whole process, we are able to achieve the control of the squirrel cage induction machine, where we are finding that the measurement of current is an essential component. The measurement of voltage may sometimes be available, or it can also be estimated on basis of the modulating signal and the converter model of the system, the inverter model of the system. However, the speed encoder can be avoided in some of the cases where we go for sensorless vector control. In some of the cases where we are finding that it is difficult to estimate because of the low speed operation and other involved factors, we may actually have the censored operation of the system. So to conclude, we have reached all the necessary, we have acquired all the necessary tools which are needed for computing or estimating or measuring the desired quantity which is involved in the control for this sensorless or censored vector control of a squirrel cage induction machine. And we can move for, say, the next level things, for example, having a simulation or hardware operation. So thank you.